The scene is a cloud stretched across light years, not bright, not aflame, but dark and nearly invisible. It is called a molecular cloud, yet its presence is less a structure and more a veil, drifting across the galaxy as a quiet patch where stars have not yet come. The dust within is fine and ancient, grains smaller than the width of light's shortest waves, coated in mantles of ice built layer by layer from water, carbon monoxide and methanol. They absorb the starlight that falls upon them, scattering the blue away, muting the red, and leaving only shadow. In these regions, the temperature falls to 10 degrees above absolute zero, cold enough for molecules to survive undisturbed, cold enough for motions to slow into stillness. Only here can hydrogen pair itself into molecules that persist, sheltered from the relentless photons of the wider galaxy. The gas and dust float, drawn not yet into order, awaiting a balance to shift. Gravity already waits within, pulling always inward, but for the moment pressure still resists. The cloud is not a uniform mass, but a loose sea of density variations, regions of relative thickness embedded within a thinner fog. Every particle drifts, colliding and exchanging momentum as turbulence stirs the mixture. Invisible magnetic fields also wind through the gas, slow lines of force that couple to ions and restrain collapse, delaying what gravity would prefer to do quickly. Ironically, the most unstoppable force in the cosmos, gravity itself, begins with hesitation. Another quiet irony, where light is absent, the materials that will someday ignite it are preserved. A further irony whispers in the contrast. These places that feel empty to human eyes carry within them the only conditions where fullness of starlight can begin. The cloud is immense, yet its boundaries are fragile. Ultraviolet radiation from nearby stars gnaws at its edges, sculpting them into scallops and ripples. Deep inside, though, shielding dust protects the molecules. Carbon chains, nitrogen-bearing species, even faint traces of complex organics accumulate here in ways impossible in the open galaxy. Ice-covered dust grains act like tiny laboratories, assembling molecules in cold darkness. They remain hidden, unseen except through the long eyes of radio telescopes tuned to molecular emission lines. Observers on Earth perceive them as faint spectral fingerprints, each line a whisper of chemistry inside the dark. Stillness dominates, but the stillness is not eternal. Pressure weakens with cooling, turbulence shifts its eddies, and the balance between outward motion and inward pull gradually tips. The concept of Jean's instability defines this balance, where density and temperature decide whether a cloud fragment will hold or collapse. In a region spanning a few light years, the mass grows too great for thermal support to resist. There is no sudden signal, no flash of ignition, only a silent drift across a threshold. A knot of matter begins to contract, invisibly at first, slow enough that millions of years pass before change becomes clear. Time in these clouds stretches beyond familiar clocks. Only a few million years to arrive, yet against galactic ages, this is no time at all. Gravity waits longer than any clock, and when its patience yields collapse, the process seems almost casual. The dust thickens, visible light no longer escapes. From the outside, the knot appears as a dark blot against richer star fields, an opaque patch called a Bock globule. It is a paradox of visibility, a starless shadow that signals where stars will eventually form. Astronomers trace its outlines, but inside, events unfold beyond sight. Gas molecules bump and scatter, losing energy to the surrounding medium. Dust grains radiate their captured heat away at sub-millimeter wavelengths. Cooling quickens collapse, as heat is the only force that can oppose gravity here. The darker the interior becomes, the more certain its future. Still the mystery remains. Exactly how turbulence, magnetism, and rotation interplay in this threshold moment is not fully known. Do magnetic fields primarily delay collapse, twisting gas into filaments before allowing knots to form? Or does turbulence, chaotic and unbound, seed density variations that gravity then amplifies? Theory offers models, observations provide partial maps, but the quiet mechanics of the earliest collapse remain unsettled. A hidden stage, unreachable even with the finest instruments, leaves its outcome written only in the stars that finally appear. The cloud drifts on. Cosmic rays slip through its shielding layers, ionizing atoms here and there, sparking faint currents that tie matter to magnetic lines. These small charges, invisible but persistent, alter collapse timescales. The irony lingers. The tiniest particles, almost massless, slow the birth of the most massive structures in the sky. Another irony rests in the scales of space. A structure spanning dozens of light years will narrow itself into points of light no larger than a sun, each one's gravity condensing matter across vast distances into a fraction of a fraction. And a final irony hangs in the symmetry. Emptiness becomes crowded. Darkness becomes radiant. Quiet becomes storm. From the human vantage, what is seen is absence. A black patch against a river of stars so faint that binoculars only reveal its silhouette. Yet in that darkness, gas and dust, cooled and shielded, carry within them the promise of stellar fire. 1,000 stars might lie unborn within, each waiting on its own timescale, each destined to shape its surroundings, to scatter heavier elements back again, to begin cycles that repeat across the galaxy. No star is yet visible, no light emerges, but the stage is set. The veil of cold dust holds the silence before the beginning, as though the galaxy inhales slowly, waiting for gravity's long exhale. Filaments form like threads inside the darkness, not drawn by any hand but woven by the subtle interplay of turbulence, magnetism, and gravity. The cloud is not a uniform sea of matter, but a tangled network of density ridges, stretching across light years in quiet strands. They appear as long, narrow filaments of molecular gas, some smooth, some braided, some with knots embedded along their lengths. Observations from far infrared telescopes trace them in faint glowing outlines, each one a skeleton for future collapse. These filaments mark the first signs of structure within the fog, pathways where matter has begun to drift toward concentration. Gas flows along them as if they are channels carved through nothingness, invisible rivers in a dark ocean. It is along these threads that the process of starbirth moves forward, though slowly, almost reluctantly. The filaments arise from turbulence within the cloud, for turbulence never truly ceases. Supersonic motions ripple through the gas, creating shock fronts and compressions, while magnetic fields guide their shapes into elongated strands. Gravity amplifies the process, pulling on the denser parts, drawing material inward along the axis of the filaments. Their widths are strangely uniform, a few tenths of a light year, as if some universal rule of balance governs them, though the exact cause remains a puzzle. The irony lies in the appearance of order born from chaos, as if turbulence, the very expression of disorder, is the architect of the most delicate structure. Another irony follows. In the vacuum of interstellar space, where density is less than the best laboratory vacuums on Earth, nature sculpts patterns more intricate than any made by human hands. And a third irony sits in the timescale. The filaments hold their forms for millions of years, longer than human civilizations endure. Yet they are fleeting on cosmic scales, destined to vanish once their fragments condense into stars. Within these filaments, knots of matter begin to form. Each knot is a dense region, a prestellar core that could eventually contract further into a protostar. Dust grains inside are coated in ice, cold enough that even carbon monoxide and methane condense upon their surfaces. Chemistry continues in this frozen silence, with ultraviolet photons from distant stars occasionally striking a grain and sparking small reactions, making molecules that drift into the gas when warmed. These cores, hidden inside the filaments, are darker still, appearing as deep shadows against a backdrop of faint emission. They are the silent precursors of brilliance, the beginnings of compression that gravity will magnify. Filaments do not exist alone but branch and intersect, creating hubs where multiple strands converge. At these junctions, the density is greatest, and collapse is most likely to occur. Star clusters often emerge in these regions, as gravity collects material from several directions at once. Observers see such hubs in the Orion molecular cloud and in the Eagle Nebula, where spider webs of filaments converge into bright knots of starbirth. The analogy is of rivers feeding into lakes, though on scales incomprehensible, with matter streaming not as liquid, but as gas thinner than any vacuum chamber, flowing nevertheless along lines defined by turbulence and fields. The mystery remains as to how these filaments decide where to break into stars. Some collapse rapidly into clusters, while others remain intact for millions of years, resisting the inevitable. The relative strength of turbulence and magnetic support is debated, for both can delay gravity. Turbulence injects kinetic energy into the system, but it also decays. Magnetic fields resist collapse by channeling flows, but their precise influence depends on ionization levels that are hard to measure. The process is uncertain, not a simple switch, but a complex conversation between competing forces. This quiet uncertainty lingers, why some filaments are fertile with stars while others remain barren. Observationally, astronomers note that nearly all star-forming cores trace their origins to filaments. The Herschel Space Observatory revealed this pattern clearly, mapping cold dust emission across the galaxy. Everywhere that new stars appear, they appear first within filaments. The suggestion is that filamentary structure is not just incidental but essential. Without filaments, the diffuse gas may not concentrate sufficiently to cross the threshold of Jeans instability. The irony here is striking. The vast emptiness of a cloud can only give birth to stars once it organizes itself into narrow thread-like strands. It is the most delicate patterns, easily disrupted, that lead to the most enduring structures of the universe. Time moves slowly here. Gas flowing along filaments toward knots does so at speeds of less than a kilometer per second. Yet across light years, this flow is inevitable. Millions of years pass before the accumulation changes the balance of forces within the cores. Human imagination cannot stretch easily across such spans. One may picture it as mist drifting across a valley, thickening into droplets, then into pools. The analogy is imperfect, but offers a shadow of the process. Diffuse matter channeling itself into small concentrated centers. Like a slow whirlpool in fog, the filament leads inward, silently, invisibly, toward collapse. The filaments themselves are ephemeral. Once stars begin to ignite, their radiation and winds disperse the surrounding material. Filaments dissolve, leaving behind the newborn stars and the empty space they carved from. What remains visible to human eyes is the absence of the structure that once guided creation. The irony deepens. The most important stage in the birth of stars is the least permanent, erased by the very light it creates. All that is left to trace it are cold emissions caught by telescopes, spectral lines that reveal the structure after the fact, like footprints in sand smoothed away by tide. In the meantime, though, the filaments endure. They remain as scaffolds within the dark, invisible to the naked eye but luminous in the language of radio and infrared. They hold the weight of future stars in their quiet strands, threading the darkness with pathways of destiny. Gas, dust, ice and molecules all drift within them, bound to collapse yet resisting still, suspended in a balance that is fragile but long-lasting. The filaments are the web of becoming, the places where the galaxy writes its future in threads finer than any woven cloth. A fragile threshold waits inside the filaments, a boundary drawn not in light or shadow, but in density and temperature. When a fragment of gas grows heavy enough, when cooling has lowered its pressure so much that gravity can no longer be held back, the balance tips and collapse begins. This is described as the gene's instability, a calculation where mass, density and temperature determine the fate of a cloud. A region larger than its gene's length cannot support itself, and so it contracts. Yet in practice the process is slow, stretched across millions of years, with no sudden ignition and no visible mark. Matter that has drifted nearly motionless for eons begins to gather inward, drawn to a centre that is not yet there. The irony is stark. The collapse begins before the star exists, as though a future object commands matter to come together in anticipation. Another irony lingers in the scale, for the first moment of contraction occurs while the region is still larger than the entire solar system will one day be. And the third irony is in time itself, for what humans would call a brief collapse requires 1,000,000 years of patience. The cloud fragment cools by radiating energy, for radiation is the only way heat can escape from the depths of such a dense core. Molecules such as carbon monoxide emit in the far infrared, carrying energy away. Dust grains covered in mantles of frozen water and methanol also release heat slowly into space. Cooling ensures that collapse continues because gravity grows stronger as the center gathers mass while pressure weakens with temperature. Without cooling, collapse would stall, but in these dense cold cores, the efficiency of radiation ensures that the process proceeds. This quiet chemistry of dust and gas, unseen to human eyes, is the enabler of starbirth. Still, the process is fragile. Turbulence may stir the fragment, redistributing energy. Magnetic fields, though weakened, continue to slow contraction by resisting perpendicular motion. Ambipolar diffusion, the slow decoupling of a neutral gas from ions tied to magnetic lines, becomes important. Neutrals slip through the magnetic framework, allowing collapse to advance. Yet the timescale of this diffusion remains uncertain. Do magnetic fields prolong collapse across tens of millions of years, or do they yield more quickly? The mystery is unresolved, and it remains one of the quiet uncertainties of astrophysics. From the outside, such collapsing cores appear as dark patches against the starry background, opaque even in infrared. Astronomers mark them as Bok globules, each a few light-years across, each harbouring within it one or a few stars in the earlier stages. To human eyes they are nothing more than smudges of absence, but within them molecules swirl and gather, forming gradients that will one day become stellar centres. The paradox deepens. Darkness is the signpost of future light. At this stage, collapse is nearly isothermal. As the cloud contracts, the density increases, but the temperature remains roughly constant because radiation carries away the heat. This means the gene's mass shrinks as the density rises, allowing smaller fragments to collapse within the larger one. Fragmentation leads to multiple centers, the seeds of binary or clustered stars. Rarely does a single star form alone. For collapse almost always produces companions. The analogy is to a sheet of dew forming not a single drop but many, each drawing from the same surface of water, gas fragments into droplets of future stars, though these droplets are enormous and invisible, awaiting their long inward fall. The irony of collapse is that it proceeds silently. There is no sound in the vacuum, no shock that carries across space. Instead, each particle simply follows the pull of gravity, colliding, radiating, and settling closer to the center. Millions of years pass in this way, while from Earth the dark blot looks unchanged. Gravity works without haste, yet it never pauses. To say that collapse has begun is to speak of a process so slow that it appears as stillness. Only in retrospect, when a protostar finally shines, can one say that the threshold was crossed long ago. Within the fragment, density gradients sharpen. The outer layers remain diffuse, while the central region becomes denser and denser. Pressure slowly begins to rise, for radiation is less effective at carrying heat away once the core grows opaque. The transition comes quietly, when the center can no longer cool efficiently. Temperature rises in the innermost zone, even while the outer regions remain cold. This is the true beginning of a star, a tiny warm kernel inside a vast cold envelope. Yet still no nuclear reactions occur, only the gentle heating of gas by contraction. The quiet mystery at this stage is how many stars will form. Fragmentation is not fully predictable. Some cores split into dozens of pieces, birthing clusters, others collapse into a single massive star. The exact interplay of turbulence, cooling, and rotation is not yet fully understood. Simulations suggest pathways, but observations only show the outcome, not the process. The uncertainty is not a flaw, but a feature of cosmic birth. It is a reminder that even in regions governed by clear physical laws, complexity ensures that prediction remains incomplete. Gas continues to flow inward. Icy dust grains are carried with it, their mantles preserved in the cold. These ices contain the building blocks of chemistry that will later enrich protoplanetary disks. Already the seeds of planets are present, though not yet gathered into any solid form. The paradox is striking. The chemistry that will support life is created in the very stage when light has not yet begun. Before the star, before the warmth, before the planets. The recipes for molecules are prepared in silence, written on grains of ice drifting inward. From a human perspective, this stage is unreachable in time and space. Even the closest molecular clouds are far beyond travel, and the process itself unfolds too slowly for a single life to witness. Observers gather data in fragments, mapping spectral lines, measuring dust emission, piecing together the story across decades. The irony is quiet. Humanity studies in great detail the births of stars that no one will ever see directly, tracing processes invisible to ordinary sight, in clouds that remain dark to the eye. Yet without this patient observation, the story would remain hidden entirely. The threshold has been crossed, though no signal announces it. The cloud fragment is collapsing, gravity is guiding, cooling is permitting, and the first hidden steps toward a star are underway. It is a stage of invisibility, of fragility, and of inevitability. Where once was only a dark patch, there is now a future of light waiting within, though millions of years must pass before that promise reaches the galaxy. The fragile threshold has been passed, and collapse drifts onward in silence. Magnetic hush fills the collapsing cloud, for invisible lines of force thread the gas like quiet scaffolds, unseen yet present in every motion. These magnetic fields do not shout or flare, but whisper their influence, resisting collapse perpendicular to their orientation, guiding ions along their paths, shaping how matter falls. A collapsing cloud does not surrender wholly to gravity in an instant, because these fields hold tension within it, like cords stretched through fog. Charged particles adhere to the fields while neutral molecules slip past, creating a slow friction that is measured not in seconds or hours but in millions of years. Ambipolar diffusion is its name, the gradual uncoupling of neutral matter from charged ions bound to magnetic lines. It is a process so slow that clouds spend much of their lifetimes in waiting, held back by magnetic restraint. The irony is sharp. The smallest of charges delays the largest of collapses. Another irony lingers in perception, for to human eyes the collapse looks frozen, unchanged, though physics insist that motion never ceases. A third irony sits in the dual nature of the fields. They slow birth but may also guide it, resisting collapse yet also focusing flows toward the forming star. Observational evidence of magnetic influence comes from polarized starlight, for dust grains align their long axes perpendicular to magnetic fields, and in doing so polarize the light passing through them. Astronomers read these patterns like maps, tracing how fields thread the cloud. They reveal ordered geometries in some regions, chaotic tangles in others. In some cases, the fields seem strong enough to resist collapse entirely, while in others they appear weaker, overwhelmed by turbulence. The quiet mystery remains. How decisive is magnetic braking compared to turbulence and rotation? Simulations show differing results, and reality may be a complex mixture where none dominates. What is known is that stars cannot form without matter, shedding angular momentum, and magnetic braking may be one of the main pathways for this release. Yet no consensus fully settles the matter. The influence of the fields is subtle but widespread. Gas flows are not purely radial but channeled, streaming along field lines rather than falling directly inward. In some places, magnetic pressure holds regions aloft, preventing premature collapse. In others, the fields focus gas into filaments and sheets, seeding structures that gravity later accentuates. The paradox is clear. Invisible lines, undetectable without special instruments, sculpt the architecture of stars and planets. They are the hidden bones of the nebula, guiding without ever being seen. The analogy is of fog drifting through a forest of unseen wires, the gas bending around them, never free to move entirely at will. On human scales, the force would feel inconsequential, weaker than a magnet on a refrigerator, yet stretched across light years its influence rivals gravity. These lines of force, relics of galactic dynamos and ancient motions, persist for millions of years, threading clouds until collapse finally overcomes them. The irony deepens. Stars that will someday generate their own fierce magnetic storms are themselves shaped in youth by far gentler fields in the darkness. The interplay between gravity and magnetism produces curious patterns. When collapse grows strong enough, the field lines bend inward, dragged by the falling gas. They take on hourglass shapes, seen in polarized maps of certain star-forming cores. This geometry is a signature of balance, where gravity finally begins to dominate, but has not yet erased the magnetic presence. The image is quiet but profound, an hourglass of invisible tension holding the seeds of a star. Another irony surfaces here. Time itself is measured by hourglasses, and in these cosmic ones the flow of matter marks the clock of collapse. Still, magnetic restraint is not absolute. Neutral molecules slowly drift past, and as mass accumulates, gravity gains the advantage. Over time, the field lines are distorted, bent, and eventually carried inward toward the nascent protostar. There, the energy they carry may launch outflows and winds, feeding back into the environment. Thus, the fields that first resisted collapse later help regulate growth, allowing the protostar to shed excess angular momentum through jets. This circular irony is quiet but striking. The very force that delays a star's birth becomes the one that permits its completion. For now, though, within the collapsing core, the hush of magnetism is one of delay. Observers know that collapse could be faster if not for the fields, yet their exact role remains debated. The mystery lingers because the fields are hard to measure, faint and subtle against the backdrop of the cosmos. Only by mapping polarization across wide areas can patterns be discerned, and even then uncertainties persist. The story is one of partial clarity, where understanding is enough to know the fields matter, but not enough to quantify their full power. Time continues its slow pace. Cores linger in this magnetic restraint for millions of years, longer than any human timeline can hold, before collapse finally accelerates. To call them delayed is to speak only from the viewpoint of stars, for on galactic scales the difference is negligible. Yet from a contemplative stance the delay is meaningful, as though the universe itself insists that light should not be rushed. Only after patience, after stillness, after slow diffusion, does the collapse proceed. The irony in this rhythm is gentle. The most luminous of phenomena begins in darkness and hesitation. Human observers remain outside, tracing shadows, recording spectra, comparing models. They see in Bok globules the silhouettes of fields they cannot directly touch. The collapse is hidden, the fields invisible, the processes unspoken. Yet from these unseen lines, stars will emerge. Dust grains, ice mantles, gas molecules, ions and photons all dance to rhythms dictated by forces that cannot be seen. And within this hush, the earliest heartbeat of the star is restrained, held back until the balance shifts. The magnetic hush persists as a stage in the slow orchestration of birth. Gravity waits, turbulence stirs, fields resist, molecules cool, and time stretches. It is neither stillness nor motion, but both at once, a pause stretched across millions of years. Within this pause lies inevitability. The lines of force will yield, the collapse will advance, and light will one day burn. For now, the silence of magnetism holds sway, writing patterns into the darkness that will outlast the cloud itself. Cores in waiting lie hidden inside the filaments, dense knots that appear as opaque silhouettes against the faint glow of the galaxy. They are called prestellar cores, the places where gas and dust have crossed the threshold of gravitational binding, but have not yet ignited into visible stars. From afar they look like patches of nothingness, yet inside them molecules move in slow currents, cooled to just a few degrees above absolute zero. The dust grains within are coated in ices, each mantle grown layer by layer from water, carbon monoxide, ammonia and methanol. These frozen surfaces act as tiny laboratories where atoms meet and form new molecules that would never appear in the warmer open sky. The paradox is quiet and persistent. Chemistry more complex than the average interstellar medium occurs not in places of light and heat, but in the coldest and darkest recesses. Another irony lingers in time, for the molecules that will later enrich planets and oceans form long before any star shines. And the third irony is in vision itself, for what looks to the eye like absence is in truth the richest environment of hidden complexity. The cores are small compared to the clouds that contain them, often less than a light year across, but their densities are thousands of times higher than the surrounding medium. Observations reveal them through millimeter wavelengths, where dust emits faintly, or through absorption features against the backdrop of galactic infrared light. They are studied in quiet patience by astronomers who cannot see within them directly, but can infer their conditions from the lines of molecules such as ammonia, deuterated hydrogen, and carbon monoxide isotopes. These spectral signatures tell of temperatures near 10 Kelvin, densities of hundreds of thousands of particles per cubic centimetre, and motions that suggest collapse is either beginning or imminent. Yet the pace is slow. Even when bound by gravity, cores can linger for millions of years before advancing toward the protostellar stage. Inside these globules, matter redistributes itself. The outer layers remain cold and diffuse while the center slowly gathers mass. Radiative cooling ensures that the gas does not heat too quickly, allowing gravity to continue compressing it. The density profile steepens with a sharp rise toward the center. Eventually, the innermost region becomes opaque to its own radiation, and a hidden kernel of warmth begins to grow. This stage, invisible to direct sight, marks the earliest moments of a protostar's formation. Yet still, the majority of the core is cold, dark, and silent. The analogy is of an ember forming in the heart of ash, unseen but inevitable. Still, not every core becomes a star. Some are disrupted by turbulence or by radiation from nearby massive stars. Others may disperse before collapse completes, leaving behind no stellar remnant at all. This uncertainty is one of the quiet mysteries. Why do some cores succeed in birthing stars while others fail? Observations suggest that magnetic support, turbulence, and environmental pressure all play roles, but the full balance remains unresolved. It is a puzzle written in patterns of survival and dispersal, an unanswered question at the root of stellar statistics. The waiting stage is long enough that even molecules evolve. Simple species such as carbon monoxide may freeze out onto grains, depleting the gas. Meanwhile, nitrogen-bearing molecules like ammonia persist, becoming the primary traces of the cold core. Deuterium fractionation occurs as deuterated species become more abundant in the extreme cold, leaving chemical signatures that reveal the history of these cores. In later times, when the cores warm and collapse further, these molecules will return to the gas phase, enriching the protostellar envelope. The irony is that these frozen molecules, trapped for millions of years, will be liberated by the very star that they helped prepare. Human observers note Bok globules in nearby star-forming regions such as Taurus, Ophiuchus, and Orion. Each appears as a shadow, a blot against richer star fields. Photographs reveal their rounded shapes, sometimes with faint hints of filaments feeding into them. To the eye they are unremarkable, even featureless, but to the astrophysicist they are the crucibles of creation. What seems to be void is in truth the raw form of becoming. Here the galaxy stores its potential, as if collecting silence before releasing song. The analogy of waiting is appropriate. These cores are places of pause, stages where gravity has begun its work but has not yet completed it. They resemble seeds resting in soil, invisible until conditions shift toward growth. The soil in this analogy is the larger molecular cloud, feeding material into the core, while the seed is the gravitationally bound kernel. Unlike seeds, however, the timescales are measured not in months or years, but in millions of years, spans longer than species survive on Earth. The quietness of this timescale is profound, a rhythm so slow that human thought struggles to keep pace. The mystery deepens when considering multiplicity. Do single cores produce single stars, or do they fragment into binaries and clusters? The evidence shows both. Some cores collapse into solitary protostars, while others fragment into systems of 2, 3, or more. The balance of rotation, turbulence, and magnetic fields decides, but the details remain elusive. The outcome is significant, for most stars in the galaxy are part of multiple systems. Yet the precise origins of these multiplicities are hidden in the silence of the waiting cores. Ironic observations persist. The first is that what resists light most strongly becomes the birthplace of light itself. The second is that in order to collapse, the cores must remain cold, for warmth would support them against gravity. And the third is that even as these cores contract inward, the overwhelming majority of their mass will never become part of the star, but will instead be lost in outflows, radiation and dispersal. The efficiency of star formation is low, often only a few %, so that the galaxy must build thousands of cores to sustain its stellar population. It is an economy of abundance producing scarcity, a paradox of cosmic construction. For now, the cores remain in waiting. They are cradles of possibility, opaque knots of gas and dust, each with a fate uncertain but with gravity working silently within. No star shines there yet, no nuclear fusion has begun, but all the conditions are prepared. Dust, ice, molecules, turbulence, and magnetism hold in fragile balance, as the universe takes its long pause before continuing its steady creation. Seen from afar, they are only shadows, but shadows with the future written quietly in their depth. Gravity's patience is long beyond any human reckoning, for the cores do not collapse in moments or even in centuries, but across spans that measure in millions of years. The force is relentless, but it does not rush. Gas particles drift inward at speeds slower than the pace of a human walk, yet over distances of light years their journey is inescapable. The outer layers feed the center, and as they do the core grows denser, shaping itself into a profile that falls steadily toward a hidden heart. Dust continues to cool the gas by radiating faintly in the far infrared, so the collapse remains nearly isothermal at first, keeping temperatures steady even as density climbs. This cooling is essential, for only by shedding heat can gravity continue to draw matter inward. The irony is delicate. The collapse that leads to heat requires cooling in order to begin. Another irony rests in perception, for the slow inward drift that appears like stillness is in fact a motion more enduring than any storm. A third irony lingers in the result, for while collapse seems infinite, it is destined to end in the confinement of a finite star. As the collapse proceeds, the center becomes increasingly opaque. Photons can no longer escape as easily, and radiation is trapped, leading to the rise of temperature in the innermost region. The gas becomes pressurized, creating the beginnings of a hydrostatic core. This stage, called the first hydrostatic core, is small, no larger than the orbit of Jupiter, and lasts only a brief period in cosmic terms. Yet it is here that the transition from a diffuse clump of gas to a central object begins. The heating dust evaporates some of its ice mantles, releasing molecules back into the gas. Chemistry shifts, with water vapor and carbon monoxide rejoining the gaseous phase in the warm kernel. What was once a frozen reservoir becomes an atmosphere of new molecules. The paradox is clear. The coldest regions are needed to form the star, but warmth is the mark that a star is on its way. Still, the hydrostatic core is not yet a star. Nuclear fusion has not begun, and energy comes only from the release of gravitational potential. The envelope around the core remains vast, continuing to feed material inward. Infalling gas strikes the boundary of the growing object, creating shocks that heat it further. Layers accumulate, and the density profile steepens again. The outward appearance of the cloud, however, remains unchanged. To distant observers, the Bock globule is still only a blot of darkness, its secrets hidden within. The irony is gentle but profound. One of the most important transformations in the universe happens out of sight, concealed beneath veils of dust. The timescales here stretch perception. 1,000,000 years may pass from the first collapse to the moment the hydrostatic core forms, and another 100,000 years may pass before fusion begins. These spans are short by galactic measures, but impossibly long for creatures bound by lifetimes of decades. Gravity has no urgency. It acts with quiet certainty, pulling slowly but without pause. The analogy is of a glacier sliding down a valley, imperceptible moment to moment but inexorable over years. So too with gravity in the core, no haste, only inevitability. Astronomers trace these stages through indirect evidence. Molecular line profiles show the signature of inward motion, with asymmetries in spectral lines indicating collapse. Sub-millimeter emission maps reveal dense ridges narrowing into central knots. Occasionally a faint source in far infrared betrays the presence of a first hydrostatic core, but these are rare and fleeting. Most of the time the stage is hidden, inferred only from models and simulations. The quiet mystery persists. How long do first hydrostatic cores endure, and how many are disrupted before they become true protostars? The answers remain uncertain, for so few examples are observed. Within the collapsing envelope, dust continues to evolve. Ices sublimate in the warming regions, releasing molecules that will enrich the eventual protoplanetary disk. Organic molecules as complex as formaldehyde and methanol are liberated, mixing into the growing core. These molecules will later form part of the chemistry of planets, moons, and comets. The irony remains. Long before any world exists, its chemical inheritance is written in the dust of collapse. Another irony lies in the efficiency, for only a fraction of the envelope will join the star. Much of it will be expelled later by winds and radiation. The core that waits patiently for its birth will ultimately consume less than 1/10 of its original cradle. Gravity does not act alone in shaping the collapse. Rotation, though slight at first, becomes amplified as material moves inward. Angular momentum conserved across scales causes the gas to spin faster as it contracts. This spin slows the direct collapse, diverting material into a flattened disk. The balance between gravity's pull and angular momentum's resistance ensures that the forming star will not be alone but will carry with it a rotating envelope and eventually a disk of matter. Yet in this section gravity still dominates, patient and steady, drawing gas through every resistance. The irony of gravity's patience is that it is both endless and final. Endless because the force never stops pulling, across any distance, at any time. Final because when collapse completes, when hydrostatic equilibrium is achieved, the pull is matched by pressure and the star is born. In the interval, the universe waits in silence as though holding its breath. Light is still absent. Fusion has not begun, but the outcome is inevitable. From darkness a new source of radiance will emerge, though not yet. Human thought circles back to the patience of this process. The clouds of Orion, the dark patches of Taurus, the veils of Ophiuchus, all hold cores in waiting, some already in the grip of collapse. Each is a clock running on scales beyond comprehension, ticking not in seconds but in eons. The paradox is that the same force that pulls a pebble to the ground is the one that gathers stars, yet the scale of patience is entirely different. To drop a pebble is to see gravity at once. To watch a star form is to watch gravity extend its hand across 1,000,000 years. For now the first hydrostatic cores lie hidden within their envelopes, small warm centers inside vast cold clouds. They shine faintly in infrared, though their light is blocked from most views. They are the first visible sign that collapse has truly advanced, that gravity's patience has found its focus. Still they are waiting, for fusion has not begun. The patience continues, stretched across the ages, until one day the balance will shift and a new star will ignite. For now gravity holds its quiet vigil, infinite in reach, infinite in time, shaping silently what will one day shine. Spin in the silence grows as the core contracts, for angular momentum cannot vanish but must be conserved as the cloud falls inward. What begins as the faintest drift, perhaps only a few meters per second in rotation, across a vast fragment of the molecular cloud, becomes amplified as the radius shrinks. Just as an ice skater pulls in her arms to spin more quickly, so the collapsing gas spins faster as its scale decreases. The result is the formation of a flattened structure, a disk encircling the growing protostar, though at this stage the protostar itself is not yet truly defined. Gas streams inward, but it does not fall directly into the center. Instead it spirals, caught between the pull of gravity and the push of angular momentum, creating circular flows that spread material out in a thin rotating sheet. The irony is gentle but constant. Gravity seeks the straightest path to the center, yet angular momentum insists on curves. Another irony sits in the balance, for the same conservation law that resists collapse into a point also provides the structure from which planets may one day grow. And a third irony lies in invisibility, for these disks are dark, invisible light, blocked by dust, yet they are among the most crucial structures in cosmic architecture. Rotation does not dominate gravity, but it reshapes how gravity achieves its end. The infalling envelope channels matter into the disk, and from the disk into the center. Gas collides with itself, losing energy and slowly feeding inward. Dust grains settle toward the mid-plane, beginning the earlier stages of concentration that will later form planetesimals. Even now, before a true star shines, the seeds of planetary systems are being arranged in the shadows. This is one of the paradoxes of star formation. Planets begin to take shape before their parent star is even finished. The flow of angular momentum outward is a problem as old as the stars themselves. Without a mechanism to shed this momentum, material would stall at large radii, unable to reach the center. Theories suggest magnetic braking, turbulence, and gravitational torques in the disk as possible solutions. Magnetic fields threading the disk can transfer angular momentum outward, allowing gas to drift inward. Spiral arms within the disk can also redistribute momentum, moving energy outward and mass inward. Yet the precise mixture of processes remains uncertain. This quiet mystery is one of astrophysics' lingering puzzles. How exactly does a cloud lose enough spin to create compact stars? Without this loss, the universe would be filled with enormous whirling structures, never condensing into the concentrated points of light we see. Observations of young stellar objects reveal disks stretching tens to hundreds of astronomical units in radius. They glow faintly in millimeter wavelengths, where cold dust emits. High-resolution images from interferometers show rings, gaps, and asymmetries, though these appear at later stages. At the beginning, the disks are thick and massive, turbulent structures where matter streams in continuous spirals. The image is not one of quiet order, but of dynamic flows, though on timescales so vast that to human thought they appear still. The analogy is of a slow whirlpool in fog, turning endlessly, invisible except for the faintest hints in the spectrum. The ironies persist. First, the star that will one day blaze with its own light is nourished by darkness, fed by disks invisible in ordinary sight. Second, the planets that may orbit for billions of years are seeded in material that survives only briefly in cosmic time, fragile disks dispersed by winds and radiation. Third, the angular momentum that resists collapse is the very force that creates the structures most enduring in human imagination. The planetary systems of distant suns. The collapse continues. Material falls inward from the outer envelope, striking the disk and feeding it. shocks heat the gas, while turbulence redistributes momentum. The protostar at the center grows, still hidden, still dark in visible light but glowing faintly in infrared. It gains mass as the disk drains into it, layer by layer, ring by ring. The rate of infall is measured in fractions of a solar mass per 100,000 years, yet across the span of 1,000,000 years, a star of several solar masses can take shape. The patience of gravity is again apparent, shaping through persistence what cannot be rushed. Astronomers studying these stages face the challenge of opacity. Visible light cannot penetrate the dust, so only infrared and millimeter observations reveal the disk and the envelope. Polarized emission maps show hints of magnetic influence, while spectral lines of molecules like carbon monoxide trace rotation and infall. From these data, models are built, simulations are run, and the story of rotation in star formation is slowly pieced together. Yet uncertainties remain, especially about the relative contributions of magnetic fields and turbulence to angular momentum transport. The quiet mystery persists, unsolved despite decades of study. Inside the disk, dust grains begin to collide and stick, forming larger aggregates. Though this process belongs more properly to the later stages of planet formation, its beginnings are already present here. Submillimeter observations reveal grains larger than simple interstellar dust, indicating that growth is underway even before the star is fully born. The paradox is again clear. Structures meant for orbit are already in preparation while the central light is still hidden. The future planets are written into the spin of the disk long before their parent shines. From the outside, these systems remain dark blotches in the sky. A telescope pointed toward Taurus or Perseus reveals shadows against the stars, not luminous suns. Yet in these shadows, disks are spinning, gas is flowing, and stars are gathering mass. Human sight cannot perceive them, but human instruments extend vision, pulling whispers of radio waves into maps of unseen architecture. The irony is that the most crucial stages of star and planet formation are inaccessible to ordinary sight, requiring the invention of new senses to trace them. Rotation is not noise but necessity. Without it, collapse would be too direct, and stars would form without disks, leaving no environment for planets. With too much of it, collapse would stall, and stars would never condense. The balance between gravity and spin is delicate, yielding structures that are neither singular nor chaotic but ordered in just enough complexity to create worlds. This balance is fragile, and it is here, in the silent spin of collapsing cores, that the universe sets the stage for future systems of unimaginable diversity. For now, the cores continue to contract, their disks growing and feeding the unseen protostar. Angular momentum spreads outward, while mass drifts inward. Dust settles toward mid-planes, while shocks release frozen molecules into gas. The process is invisible, unhurried, and inevitable. Spin in the silence governs the flow, shaping the architecture of creation without ever announcing itself. The cores remain dark, but within them the quiet whirl of becoming is underway. Faint embers glow where the collapsing core has gathered enough density to trap heat, and the central protostar begins to shine softly, not with fusion, but with the release of gravitational energy. Each particle that falls inward loses potential energy, and that energy is converted into heat at the core. The warmth radiates outward, escaping through veils of dust, visible only at long wavelengths. To the eye it remains hidden, still dark against the sky, but in the far infrared and submillimeter ranges it glimmers as a faint ember in the night. This is the protostar stage, a period lasting hundreds of thousands of years, when the star has taken form but has not yet ignited nuclear fire. The irony is quiet. The star exists before it is truly a star. Another irony sits in the invisibility, for the first light of the star cannot be seen in the spectrum most familiar to human eyes. A third irony is that the glow-marking birth is not from creation but from collapse, the light of falling rather than burning. The protostar is surrounded by an envelope of infalling gas and dust, feeding it through a rotating disk. The envelope is vast, stretching thousands of astronomical units, while the disk narrows to hundreds. Material continues to stream inward, colliding, shocking and heating as it joins the central body. The protostar grows in mass as the envelope thins, though most of the original cloud will never become part of the star. Much is carried away by outflows and winds, or dispersed by radiation when the star brightens. The efficiency of star formation remains low, only a few % of the original mass becoming stellar light. This paradox of abundance producing scarcity is written into every newborn star. Within the protostar, the temperature climbs as density increases. Eventually it reaches thousands of degrees Kelvin, not enough for fusion but sufficient to alter the chemistry around it. Dust grains near the center lose their icy mantles, releasing water, carbon monoxide and organics back into the gas phase. These molecules radiate in rotational lines, signaling their presence to distant observers. The chemistry of collapse thus leaves its signature, a faint code read by radio telescopes. Molecules such as methanol and formaldehyde trace the warming zones, while deuterated species record the earlier cold history. The paradox is again visible. The chemical record of a star's life begins long before the star itself is luminous. The protostar is unstable in appearance. Accretion occurs in bursts, with matter sometimes falling inward in sudden surges. Shocks heat the surface, and luminosity spikes. Between these events, the star dims, glowing faintly again. Observations of young stellar objects confirm this variability, with sudden brightening episodes known as FU Orionis events, when accretion surges by orders of magnitude. These bursts reveal the unsteady nature of growth, the uneven feeding of the star by its disk. The irony here is simple. The most steady lights in the sky begin as flickering, unstable embers. The quiet mystery of this stage lies in the regulation of accretion. Why does material fall in bursts rather than smoothly? Some models suggest instabilities in the disk, with spiral arms driving inward flows. Others propose that magnetic reconnection events trigger surges. Observations remain incomplete, and no single mechanism fully explains the variability. The universe keeps its secret, allowing only glimpses of the process through sudden brightening and fading. The protostar's presence alters its surroundings. Its light, faint though it is, begins to warm the envelope, creating gradients in temperature that change the chemistry of ices and molecules. Jets and outflows emerge, carving channels through the cloud. These jets, though not yet strong, begin to clear pathways in the dark material. The paradox is constant. The star grows only by consuming, yet it survives only by expelling. Infall and outflow are paired, feeding the star while also shaping the nebula. Observers on Earth detect protostars in regions such as Orion, Perseus and Ophiuchus. They appear as point sources in infrared maps, invisible in visible light but clear when dust is transparent to longer wavelengths. In many cases they're buried so deeply that even infrared fails, and only submillimeter observations reveal them. Human eyes cannot perceive them directly, yet their faint embers are recorded by instruments. The irony deepens. The first stars to emerge in the galaxy after the Big Bang were invisible to sight, and the first stars in any nebula today remain invisible until fusion begins. Time flows slowly in the protostellar stage. Hundreds of thousands of years pass while the star gathers mass, accretes, and radiates its faint heat. From the human perspective, nothing changes. From the cosmic perspective, this is a brief stage, soon to pass. The patience of gravity remains the rhythm, steady and enduring, indifferent to the measure of mortal years. The analogy is of a coal buried in ash, glowing faintly, waiting for the moment when the fire will catch. The fire in this case is hydrogen fusion, but that lies ahead. For now the ember stage holds, quiet and dim. Ironies accumulate in the silence. One is that collapse, a process of falling inward, produces light that radiates outward. Another is that the first sign of a star is not its flame but its shadow, for the surrounding envelope is more visible than the core. The third is that the protostar, though the focus of the process is defined by what it is not yet a star, not yet burning, not yet stable. Its identity lies in becoming rather than being. Still, the faint ember glows. It warms its immediate surroundings, stirs chemistry, drives flows, and marks the point where gravity's patience has taken form. The envelope continues to fall, the disk continues to spin, and the protostar continues to grow. In the silence of the molecular cloud, a hidden light persists, faint but enduring, the prelude to radiance. It is not visible to the eye, not luminous in the way of stars, but it is real, steady in its own slow rhythm. The universe holds this stage gently, waiting for the ember to ignite fully. Outflows in the dark emerge as the protostar gathers mass, for not all material that falls inward can remain. Some of the gas, guided by twisted magnetic fields and rotating flows, is launched outward in narrow streams. These bipolar outflows pierce through the surrounding envelope, carving channels through the dense cloud. Jets of ionized gas shoot from the poles of the protostar, sometimes extending light years into space, glowing faintly where they collide with the surrounding medium. They are paradoxical structures, for the star feeds and expels at the same time. Without the loss of angular momentum carried away in these outflows, material could not accrete onto the center. The irony is persistent. The star grows by throwing matter away. Another irony is that what seems destructive, the clearing of gas, creates the very conditions that allow light to escape. A third irony lies in contrast, for the earlier signs of young stars come not from the hidden stars themselves, but from the wounds they carve in their natal clouds. The physics of these jets is subtle. As material falls onto the disk, some of it couples to magnetic field lines anchored in the rotating structure. Twisting and tension launch gas along the open field lines at high velocities. The collimation of the flow is remarkable, producing narrow beams that persist across vast distances. Shocks occur where the jets meet ambient gas, heating it and causing emission in optical and infrared lines. These shocks are visible as knots and arcs, called Herbig-Haro objects, glowing faintly in otherwise dark regions. To the naked eye, the star is unseen, but its presence is betrayed by these distant sparks of impact. The mystery of how outflows are launched remains partly unsolved. Magnetocentrifugal acceleration, magnetic pressure gradients, and disk winds are all proposed, but no single mechanism is universally accepted. Observations reveal jets with speeds of hundreds of kilometers per second, narrow and stable over thousands of years, yet models struggle to reproduce all details. It is one of the quiet questions of astrophysics, unresolved but slowly approached through theory and observation. The paradox is striking. Humanity sees the jets clearly, but does not yet fully know how they are made. The outflows alter the environment dramatically. They sweep up gas, create cavities, and clear pathways through the envelope. Radiation from the protostar, once blocked by dust, now has channels through which it can escape. The surrounding core is no longer entirely opaque, and light begins to filter outward. The outflows regulate growth, limiting the final mass of the star by removing material that otherwise would have fallen inward. In clustered regions, they also influence neighboring cores, compressing or dispersing gas, sometimes triggering collapse, sometimes preventing it. The irony is delicate. The chaos of jets creates order by shaping the architecture of star-forming regions. Herbig-Haro objects mark the collisions of jets with dense clumps of gas. They glow in forbidden emission lines of oxygen and sulfur, shining faintly in visible light even when the protostar itself remains hidden. These glowing knots drift slowly outward, tracing the history of the outflows over thousands of years. Astronomers map their motions, reconstructing the episodic nature of the jets. The flow is not steady but pulsed, with bursts of stronger ejection interspersed with quieter phases. This mirrors the variability of accretion, linking the feeding of the star to the expulsion of matter. The irony persists. The star's appetite and its rejection of material are bound together in rhythm. The scale of the outflows is immense compared to the size of the star. A protostar smaller than the Sun can drive jets that extend for light years, visible across parsecs of space. The energy in these flows shapes entire clouds, stirring turbulence and redistributing momentum. The analogy is of a candle flame pushing smoke across a room, yet here the candle is a hidden ember, and the smoke trails for trillions of kilometers. What seems small at the center has consequences across the surrounding nebula. For human observers, outflows are often the first signs of young stars in distant regions. Telescopes capture glowing knots, arcs, and jets in visible and infrared, even when the source is too faint to see. The jets stand as announcements of unseen beginnings, written in streaks of light across the darkness. The irony is sharp. The absence of the star itself highlights the presence of the structures it creates. The chemistry of the outflow regions is also altered. Shocks heat the gas, driving molecules into new reactions. Water, carbon monoxide, and silicon monoxide become abundant in these shocked zones. Observations detect mass emission, strong microwave amplification of radiation by molecules aligned in the shocks. These masses serve as beacons, pointing directly to regions of outflow impact. Thus, the hidden processes of protostars are traced not by their centers, but by the signatures of their collisions. The quiet mystery of outflow longevity remains. How long do these jets persist? And when do they fade? Some suggest they last only during the main accretion phase, vanishing once the star stabilizes. Others propose they continue intermittently, fed by disk instabilities even after the star has begun nuclear burning. The evidence is mixed, and the question is not yet closed. The universe keeps its answer slow, as it does with all processes of becoming. Ironies multiply in this stage. One is that the protostar becomes visible to instruments not through its own light, but through the destruction it causes in its surroundings. Another is that the clearing of material, which seems like a loss, is what allows the star eventually to shine freely. The third is that these dramatic jets, bright and energetic, are in truth essential acts of balance, quiet regulators of the star's growth. For now, the outflows continue, silent in the vacuum, narrow streams of gas cutting through the dark. They announce the protostar's presence without revealing it. They shape the cloud, alter chemistry, and carry away angular momentum. They are paradoxes of growth through loss, destruction as creation, and silence as testimony. Outflows in the dark are the first visible handwriting of the star, written not in brilliance but in motion. a script across the sky that foretells light to come. Shadows and sparks intermingle in the young stellar environment as the narrow jets of gas strike the denser knots of the surrounding cloud. Where the streams collide, shock waves compress and heat the gas, creating faint glowing structures called Herbig Haro objects. These are not stars though they shine, nor clouds though they drift, but transient patches of light where energy is converted into visible form. They glow in emission lines of hydrogen, oxygen and sulfur, faint beacons of impact in otherwise dark nebulae. To the human eye through a telescope they appear as small smudges or arcs, but to the astrophysicist they are records of collisions and markers of a star's hidden presence. The irony is quiet yet striking. The star itself is concealed in dust and shadow, while the violence of its outflow illuminates the space around it. Another irony lingers in their brevity, for these sparks last only tens of thousands of years, a blink in stellar terms. A third irony rests in contrast, for the structures most delicate to the eye are forged in shocks that tear through gas at hundreds of kilometers per second. The jets carve cavities, channeling material away and allowing radiation to escape. These hollowed-out spaces form the first windows in the dense envelope, patches where starlight filters through once the core begins to shine more strongly. In the meantime, the Herbig Haro objects provide testimony of the jet's path. Each knot in the stream is a fossil of a burst of ejection, carrying memory of the accretion variability within the disk. Observations of their spacing and speed reveal pulsed histories, bursts of greater or lesser force that span thousands of years. The young star is hidden, but its rhythm is written in the string of luminous knots it leaves behind. The mystery persists as to how jets remain collimated across such distances. Magnetic fields appear essential, threading the disk and guiding flows outward. Yet details remain unresolved, for the balance between centrifugal acceleration, pressure gradients, and magnetic confinement is delicate. Simulations reproduce some features but not all. Observations provide glimpses but not complete understanding. The question remains quietly open. Why do some jets remain narrow for light years, while others flare into diffuse winds? The universe offers no final answer, only more structures to trace. Around these glowing knots lie shadows cast by dense clumps of gas. The same outflows that illuminate create silhouettes, backlit by scattered light and emission. Proplyds, or protoplanetary disks seen in silhouette, are revealed against bright nebula backgrounds, dark tear-shaped forms with faint tails pointing away from nearby massive stars. They are both shadows and survivors, disks of material that may someday form planets, enduring under the erosion of radiation. Here again irony holds. The darkness of the disk reveals the possibility of future light from planets and worlds. Herbig Haro objects are catalogued in hundreds, scattered across star-forming regions from Orion to Taurus. Some appear as chains, others as isolated sparks, some aligned, others curved by motion through surrounding gas. They are fragile to view yet immense in scale, each extending a fraction of a light year. Their lifetimes are fleeting, for shocks cool, flows move, and structures dissipate. The transient nature of these sparks contrasts with the permanence of the star they mark. It is as if the galaxy writes in temporary strokes, erasing them quickly, leaving only the star as the final word. For human observers, they are among the few visible signs of the hidden process of starbirth. Long before the protostar emerges in optical light, these sparks betray its presence. The irony is again clear. One of the earliest visible phenomena of a new star is not the star itself, but the scars it leaves in its surroundings. Light is born not from the center but from the edges where motion collides with resistance. The star is invisible, the shadows remain, and the sparks testify. In these shocked regions, chemistry shifts. Molecules are dissociated by collisions and reformed in new configurations. The gas glows in forbidden lines, transitions that cannot occur in dense environments but thrive in the thin, shocked medium. These lines carry information about density, temperature, and velocity, allowing astronomers to reconstruct the physics of the shocks. The study of Herbig-Haro objects thus becomes a study of the hidden protostar, inferred through the impacts of its outflows. The paradox is deep. The central star is known not directly but by its footprints on the surrounding gas. The presence of both shadows and sparks creates a dual image of star birth. On one side is concealment, the opaque dust that hides the star from view. On the other is revelation, the faint emission from shocks that expose its activity. Together they create a portrait of becoming that is both hidden and announced, veiled and revealed. This balance is one of the quiet rhythms of the cosmos, where nothing emerges all at once but only in fragments, partial glimpses before completion. The timescales again are long. Thousands of years pass between bursts, tens of thousands mark the lives of the shocks, while millions pass before the star stabilizes. Human lives cannot witness the changes in a single object, but can only compare generations of images and measure shifts across decades. The irony of perception is sharp. Astrophysics studies the ephemeral by recording stillness, reconstructing motion from absence. The sparks appear frozen, yet they are always moving. In the great star-forming regions, shadows and sparks intermingle in numbers beyond counting. Dark filaments lace across glowing gas. Herbig-Haro objects flicker at their ends, and unseen stars drive the flows. Each shadow is a promise of hidden growth, each spark a record of outward force. Together they form the intermediate stage of star birth, when the star is still concealed but already shaping its world. They are the dialogue of darkness and light, destruction and creation, concealment and revelation. For now the protostar remains unseen, its fusion still dormant, its light still muted by dust. Yet the environment already carries its mark. Shadows cast by disks, sparks from shocks, and cavities from outflows all testify that the star is real, growing, and inevitable. The irony of this stage is that the most telling signs of a star's presence come not from itself, but from what it changes around it. The shadows and sparks are peripheral, yet they are the heralds of a new light. In silence and darkness, the galaxy writes its announcement in subtle glowing lines across the canvas of the cloud, while the star continues its hidden growth at the center. The luminous cage forms when the first massive protostars ignite, their light strong enough to ionize the gas surrounding them. Ultraviolet photons strike hydrogen atoms, stripping electrons away and creating large volumes of plasma known as H2 regions. These regions glow in emission lines, visible across thousands of light years as pink or red nebulosity, their brilliance contrasting with the dark molecular clouds nearby. To human eyes through telescopes, they are the most familiar symbols of star birth, shining expanses like the Orion Nebula or the Carina Nebula. Yet the beauty conceals a paradox. The same radiation that illuminates the cloud also erodes it, dispersing the material from which new stars might have formed. The irony is sharp. Stars announce their birth by destroying their own cradle. Another irony lingers in their geometry, for the radiant spheres appear like cages that both reveal and confine. A third irony rests in time, for the most massive stars live only a few million years, yet their light shapes environments for hundreds of millions after they are gone. The physics of ionization is precise but simple. When hydrogen absorbs a photon with energy greater than 13.6 electron volts, it loses its electron, becoming ionized. Recombination follows as electrons and protons reunite, emitting photons in discrete lines, most famously the hydrogen alpha line at 656 nanometers. This continuous cycle fills the region with diffuse emission, a glow that spreads in all directions. The balance between ionization and recombination determines the size and brightness of the H2 region, expanding outward until equilibrium is reached with the surrounding neutral gas. Observers see this as a luminous bubble, its edges sharp where photons are absorbed, its interior filled with diffuse plasma. The formation of such regions transforms the molecular cloud. The expanding ionized gas pushes against the surrounding neutral material, creating shells of compression. These shells can trigger new collapse in nearby filaments, igniting further rounds of star formation. Thus, the destructive radiance also creates, spreading birth outward even as it erodes. The paradox is evident. The light that disperses also gathers, the destruction that clears also seeds. This feedback cycle is central to the life of galaxies, regulating the pace of stellar generation across the spiral arms. The quiet mystery is the efficiency of this feedback. How many stars are triggered by expanding H2 regions, and how many are prevented? Observations suggest both outcomes, but the balance is uncertain. Some regions show chains of young stars along ionization fronts, clear signs of triggered collapse. Others show dispersal without creation, the material swept away before it could condense. Models vary, and no single rule holds across all nebulae. The galaxy writes its story differently in each cloud, a variability that defies prediction. Inside the luminous cage, protoplanetary disks are exposed to intense radiation. In the Orion Nebula, hundreds of proplyds have been imaged, each a small disk of gas and dust surrounding a young star, with comet-like tails streaming away under ultraviolet light. These disks are fragile, eroded from the outside inward, their lifetime shortened by the harsh environment. Yet some survive long enough to form planets, creating systems shaped by their luminous neighbours. The irony here is that the most brilliant stars in a region often reduce the chances for planets to form around their companions, while fainter stars in quieter environments preserve their disks more easily. The cages of light expand over time, tens of light years across, eating into the molecular cloud until the gas is dispersed. The newborn stars then remain exposed, shining in open clusters where once they were hidden. The luminous nebula fades as fuel is exhausted, leaving behind only the stars it created. This transformation is one of the most visible in the galaxy. Clouds dissolving into clusters, dark veils replaced by radiant arcs. To human eyes, these are symbols of beauty, but to the cosmos they are transitions, the inevitable dispersal of natal material into the wider medium. The irony deepens in the lives of massive stars themselves. They are the architects of the luminous cages, yet they live short lives and die violently as supernovae. In their brief spans they create and destroy, shaping the environment and then scattering heavy elements into space. Their radiation, winds and explosions regulate star formation on scales far beyond their lifetimes. The paradox is complete. The most fleeting stars exert the most enduring influence. From Earth, the luminous cages are among the most studied regions of the sky. The Orion Nebula lies only 1,300 light-years away, and is visible to the naked eye as a faint patch in Orion's sword. Within it, thousands of young stars shine, their disks sculpted by the trapezium cluster at the center. The Carina Nebula, larger and farther, contains massive stars whose winds carve dramatic pillars and cavities. The Eagle Nebula, with its famous pillars of creation, shows towering columns of gas eroded by radiation, each pillar a testament to the balance between creation and destruction. These images captivate, but they also testify to the physics of ionization, expansion, and erosion. The quiet analogy is of a lamp held within mist. The light reveals the mist, illuminating its structure, but in doing so it also evaporates it. The more brilliant the lamp, the faster the mist is dispersed. In star-forming regions, the lamp is ultraviolet radiation. The mist is molecular gas, and the consequence is both beauty and impermanence. What human eyes see as timeless is in truth fleeting, a stage that lasts only a few million years before dispersal. The luminous cage is thus both cradle and coffin for the surrounding cloud. It marks the transition from hidden birth to exposed youth, from darkness to brilliance, from possibility to permanence. The irony of visibility is strongest here. The nebula is most beautiful when it's dying, its destruction the very process that allows it to be seen. Long after it fades, the stars remain, but the cage of light will be gone. For now it shines, a glowing shell of hydrogen, lit by the relentless fire of the youngest massive stars, shaping the galaxy in silence and inevitability. Triggered seeds emerge along the advancing edges of luminous cages, where the expanding ionized gas compresses the neutral molecular cloud. As the H2 region swells outward, it sweeps up a shell of dense material, pressing filaments and clumps into greater concentration. Where the pressure grows sufficient, collapse begins anew, and new stars are seeded. This process, called triggered star formation, turns destruction into creation, one generation of stars giving rise to the next. The paradox is vivid. Radiation that disperses the parent cloud also fosters its continuation. Another irony lies in timing, for the lifetimes of massive stars are so short that they begin to trigger collapse in neighbours before their own light has fully stabilized. A third irony rests in causality, for the brightest stars, those most visible, are not only the products of earlier collapse, but also the initiators of later collapse, linking generations together in quiet succession. The physics of triggering follows clear principles. The expanding ionized front acts like a piston, driving shocks into the cold neutral gas. Pressure rises in the compressed layers, sometimes exceeding the gene's limit, allowing gravitational collapse. This is known as the collect and collapse process, where swept-up shells break into fragments that become new cores. Another pathway is radiation-driven implosion, where pre-existing clumps are compressed by ionization fronts until they collapse. Both mechanisms are observed in nebulae across the galaxy, from Orion to Carina to the Tarantula Nebula in the Large Magellanic Cloud. Observers detect young stellar objects forming at the edges of bright ionization fronts, their positions evidence of triggered birth. Yet the efficiency of this process remains uncertain. Not all compressed gas collapses. Much is dispersed before it can form stars. The balance between creation and dispersal depends on local conditions, the strength of radiation, the density of the cloud, and the orientation of magnetic fields. Some regions become fertile, birthing clusters of new stars at their edges, while others are stripped bare, their gas scattered into interstellar space without collapse. The quiet mystery persists. How often does triggering truly create stars, and how much of star formation owes its origin to this mechanism rather than spontaneous collapse? The answer remains incomplete, hidden in statistics too large to measure and processes too subtle to resolve. In iconic nebulae, the evidence of triggered seeds is visible. The pillars of creation in the Eagle Nebula show towering columns of gas eroded by radiation. At their tips, dense clumps glow with the heat of embedded protostars, likely compressed into collapse by the advancing ionization front. Similar features are seen in the Carina Nebula, where bright ridges and knots of star formation appear precisely where radiation-driven shocks impinge on dense gas. These images reveal the interplay of erosion and creation, the simultaneous dispersal of gas and the concentration of cores. The paradox is again present. The same pillars that are dissolving hold within them the seeds of new stars. The timescales of triggered star formation are long compared to human lifetimes, but brief compared to cosmic ages. Ionization fronts expand over millions of years, and collapse within compressed clumps may take a similar span. Thus, one generation of stars can give rise to another within a few million years, overlapping in their lifetimes. Clusters may therefore contain stars of multiple ages, layered records of successive rounds of birth. Observations of age spreads within clusters support this picture, though the details remain debated. The analogy is of ripples spreading in water, each crest producing a smaller crest beyond, the pattern propagating outward. The irony of triggered collapse lies in its fragility. Compression must be strong enough to induce collapse, but not so strong that the clump is dispersed. The balance is delicate, and often only a fraction of clumps succeed. Yet even this fraction is sufficient to sustain star formation across galaxies, as massive stars seed the birth of their successors. It is an economy of succession, destruction as inheritance, light giving rise to more light. Human observers trace triggered seeds through the alignment of young stellar objects along ionization fronts. Infrared surveys reveal protostars clustered near bright rims, while millimeter observations show dense cores forming at compressed edges. These data suggest that triggering is widespread, though not universal. In some nebulae, age gradients point directly to sequential star formation driven by expansion. In others, no such pattern appears, and spontaneous collapse dominates. The universe offers both, not one or the other, and the mixture defies simple classification. Triggered collapse also affects the distribution of stellar masses. Compressed gas may preferentially form clusters rather than isolated stars, and massive stars themselves may be more likely to arise in triggered environments. If true, this would link the most luminous stars to cycles of feedback, ensuring that their presence not only ends clouds but begins new stars. The quiet mystery is whether this bias is real or only apparent. The data remain incomplete, but the suggestion continues to intrigue astronomers, hinting at deeper connections between light and its propagation. The irony of perspective is also present. To human eyes, the edges of nebulae appear as the most beautiful regions, pillars, ridges, bright arcs. Yet these are precisely the places where destruction is most intense. Within them, however, new stars are forming, making the beauty both ephemeral and fertile. The nebulae photographed by telescopes are records not of permanence but of transition, caught in the act of being consumed and renewed. The analogy is of fire spreading in a forest. The flames consume, yet in their aftermath seeds germinate, nourished by cleared soil and released nutrients. So too with ionization fronts, burning gas away while compressing what remains into fertile collapse. The paradox is gentle but profound. Death and birth are not separate processes but simultaneous expressions of the same feedback. For now, triggered seeds continue to appear along luminous shells, compressed clumps collapsing into protostars while surrounding gas disperses. The cycle of star formation extends outward, generation by generation, as light creates more light. Shadows deepen, sparks glow, shells expand, and clumps collapse. The universe writes its continuity in these quiet rhythms, linking stars across time not only by inheritance of matter, but by inheritance of gravity and light. Triggered collapse ensures that one birth is never solitary, but part of an unbroken chain, stretching across clouds, clusters, and galaxies. Crowded nurseries unfold within the vast molecular clouds, where stars seldom emerge alone but arrive together in groups of dozens, hundreds, or even thousands. The reason lies in the scale of collapse, for filaments fragment into multiple cores, and each core can yield more than one protostar. The result is clustered star formation, the dominant mode of birth in the galaxy. Solitary stars exist, but they are rare compared to the collective gatherings of light that fill the spiral arms. The irony is gentle. The stars that appear most individual in the sky were almost always born in company. Another irony rests in time, for the clusters that begin so tightly bound soon disperse into the galaxy, their stars wandering apart, leaving no trace of their shared origin. A third irony rests in proportion, for most of the galaxy's mass is locked into small faint stars, while human eyes are drawn to the few brilliant ones that will die young. Within these nurseries, the distribution of stellar masses follows a pattern known as the initial mass function. It shows that low-mass stars are far more common than massive ones, though the few massive stars dominate the light and energy. For every star heavier than 20 times the mass of the Sun, thousands of red dwarfs form, each only a fraction of the Sun's mass. The reason for this distribution is not fully known. Turbulence, fragmentation, accretion rates, and feedback all play roles, but no single factor explains the balance. The quiet mystery remains. Why does the universe favor small stars so overwhelmingly, and what determines the slope of the mass function? The answer is essential, for it shapes the structure and evolution of galaxies, yet it is not fully resolved. Clusters are dynamic environments. Stars interact through gravity, perturbing one another's orbits and scattering disks. Close encounters may truncate or even strip circumstellar disks, influencing the potential for planet formation. At the same time, the shared environment bathes young stars in radiation from massive companions, eroding some disks and altering others. The irony of birth in a crowded nursery is that companionship can nurture and hinder at once. The same proximity that creates shared origins may limit the futures of worlds. Observations of nearby clusters such as the Orion Nebula cluster reveal the density of these regions. Thousands of stars occupy a space only a few light-years across, glowing in infrared and X-ray light, each at a different stage of formation. Some are still deeply embedded in envelopes, others are young protostars with disks, while others have already cleared their surroundings. The mixture testifies to the overlapping nature of star formation, where collapse, accretion, and dispersal occur side by side. The cluster is both crowded and diverse, a microcosm of stellar evolution. Multiplicity is another outcome of clustered birth. Binary and multiple systems are common, formed through fragmentation of collapsing cores and interactions within clusters. Observations show that a significant fraction of stars exist in pairs or groups, bound gravitationally from birth, yet the details vary with mass. Massive stars are more often in binaries, while low-mass stars more often remain solitary. The paradox is evident. The brightest stars in the sky are the least likely to stand alone, while the faintest stars wander mostly by themselves. The cluster environment also influences stellar dynamics on long timescales. Many clusters disperse within a few 100 million years, their stars scattered into the galactic disk. Others remain bound as open clusters, surviving for billions of years. The Pleiades, the Hyades, and other open clusters visible in the night sky are remnants of such nurseries, preserved long after their natal clouds were dispersed. Globular clusters, larger and older, are still more enduring, though their origins may differ. The irony lies in the fate of companions. Stars born together seldom remain together, their kinship erased by time, yet the memory is written in their shared chemical compositions. The analogy is of a meadow of flowers blooming together. From afar the meadow seems a unity, but each flower eventually scatters its seeds to the wind, leaving only the field behind. So too with clusters, born together, dispersed apart, their unity temporary but their presence unmistakable while it lasts. The crowded nurseries are turbulent and luminous. Outflows from protostars collide, feedback from massive stars sculpts cavities, and radiation fields bathe the cluster. Yet within this dynamic environment, stars achieve stability. Fusion begins in their cores, and they settle onto the main sequence. The nebulae around them gradually dissipate, leaving the cluster exposed. The beauty of the Orion Nebula, seen today, is thus transient, a brief stage when stars and cloud coexist visibly. In a few million years the gas will be gone, leaving only the stars shining against the darkness. The ironies of clustered birth persist. First, the galaxy is filled with stars that seem solitary, yet their origins were in company. Second, the light of clusters is dominated by the rarest stars, while the majority of faint companions remain nearly invisible. Third, the structures most permanent in the galaxy, the long-lived red dwarfs, are born in the most fleeting environments, dispersing almost as soon as they begin. The crowded nurseries are essential to galactic ecology. They recycle matter, distribute energy, and populate the disk with stars of all masses. Their turbulence seeds diversity, their feedback regulates formation, and their dispersal ensures mixing. They are both the beginning of stellar life and the architects of galactic structure. To human sight they appear as glowing patches in the sky, nebulae of colour and shape. To physics they are regions of pressure, density, temperature and feedback. To time they are but brief chapters, passing quickly into dispersal. For now they endure in their crowded state, stars packed closely in veils of gas and dust, companions in their first million years. Their light, though faint to distant eyes, fills the nebula with subtle glow. Their futures will diverge, their paths will scatter, but in this moment they share a cradle. The crowded nurseries are temporary congregations, fragile yet fertile, the beginning of countless journeys of light across the galaxy. Thinning veils surround the young stars as radiation and winds begin to disperse the remnants of their natal clouds. What was once a dense, opaque shroud of dust and gas becomes increasingly transparent, revealing the stars within. The process is neither sudden nor complete, but gradual, a peeling away of layers over hundreds of thousands of years. Ultraviolet light from massive stars ionizes the surfaces of disks and envelopes, driving gas outward in slow streams. This photoevaporation sculpts fragile structures known as proplids, disks silhouetted against bright nebular backgrounds, their outer edges glowing as they are stripped away. The irony is evident. The very light that announces the star's emergence also erodes the material from which planets might form. Another irony rests in visibility, for the disks are seen most clearly when they are in the process of being destroyed. A third irony lingers in survival, for though many disks are lost, a few endure long enough to seed planets, and these survivors are the foundations of worlds. The physics of photoevaporation is straightforward. Ultraviolet photons heat the upper layers of a disk or envelope, raising temperatures until gas becomes unbound and flows away. The rate of this loss depends on the intensity of radiation and the distance from the source. In rich clusters such as Orion, where massive stars dominate the environment, disks may be eroded within a few million years. In quieter regions, disks survive longer, perhaps 10 million years or more, giving planets time to grow. The paradox is stark. The environment most luminous and dramatic is least friendly to planets, while the faint outskirts, less striking to the eye, are where planetary systems most often emerge. Observations of proplids in Orion provide direct evidence of this process. Hundreds of small disks are seen as dark silhouettes or glowing teardrop shapes, their tails pointing away from the trapezium stars at the center. They are real-time records of photoevaporation, the stripping of gas by ultraviolet light. Some are nearly gone, their disks reduced to tiny remnants. Others are still substantial, with enough mass to form systems of planets. The variety shows the uneven influence of environment, where chance position relative to massive stars determines survival. The quiet mystery is how many of these disks endure long enough for planets like Earth to form. Statistics suggest survival rates are modest, yet planets exist in abundance, meaning the process is efficient enough despite the losses. The thinning veils also reveal the diversity of young stars. Some emerge as solitary suns, others as binaries, others as members of crowded clusters. The dispersal of gas allows their light to escape, transforming regions once opaque into glowing cavities. Nebulae that seemed solid dissolve into filaments and shells, leaving the stars exposed. The irony of beauty is present here. The shapes most admired in nebular images, the pillars, arcs, and wisps, are transient, lasting only as long as the gas is being eroded. Once the gas is gone, the forms vanish, leaving only the stars, permanent but less striking to the human eye. The process of disk dispersal is complex. In addition to photoevaporation, stellar winds and jets continue to remove material. Accretion diminishes as the envelope is exhausted and the disk thins. Viscous evolution spreads material outward, even as inner regions drain inward. Gaps may form, created by turbulence or by the earlier stages of planet growth. By the time the disk has thinned significantly, the star has settled into stability, burning hydrogen in its core. Yet the fate of planets depends on whether the disk survived long enough to allow solids to accumulate and cores to form. The irony is clear. The most enduring structures, planets, depend on the most fragile disks, surviving the harshest early environment. In some cases, external radiation creates comet-like tails of gas trailing from disks. These structures, observed in Orion and Carina, are among the most direct demonstrations of the destructive influence of massive stars on their neighbours. Yet not all is loss. The compression of gas in the inner disks may accelerate planet formation, condensing solids before gas escapes. Thus destruction and creation intertwine once again, erosion speeding up the very processes it threatens to halt. The analogy is of a sculptor chiseling away at stone, the act of destruction creating form. The quiet mystery remains how much of planetary diversity owes itself to these early processes. Are the architectures of planetary systems, numbers of planets, their masses, their orbits, set by survival against erosion or by intrinsic disk properties? Observations of exoplanets reveal wide variety, from hot Jupiters close to their stars to systems of small rocky worlds. The connection between these outcomes and early disk evolution is still being traced. The paradox is that the most fragile beginnings shape the most enduring futures. As the veils thin, stars emerge visibly. The nebula that once concealed them becomes translucent, its gas glowing in emission lines as it disperses. Open clusters appear, their stars shining freely against the backdrop of the galaxy. The transition is complete when the gas has gone, leaving the cluster exposed. Yet even then, dispersal continues as the cluster itself begins to loosen and spread across the galactic disk. The irony of visibility remains. Stars are most admired when freshly revealed, yet their companionship soon dissolves and they wander apart unseen. Human observers gazing through telescopes capture these thinning veils in detail. The Hubble Space Telescope imaged the Pruplids of Orion, each a tiny world in the making or unmaking. The James Webb Space Telescope now reveals disks in infrared, tracing their composition, structure, and survival. These glimpses confirm the fragility and resilience of disks, their fate written in light and shadow. What the human eye sees as fleeting shapes are in truth decisive stages in the creation of planets and systems. The thinning veils are thus both ending and beginning. They mark the dispersal of the parent cloud, the exposure of the stars, and the narrowing of disks into fragile remnants. They also mark the preparation for planets, the sculpting of the material that will endure long after the gas is gone. The ironies hold. Destruction reveals, erosion creates, fragility yields permanence. The stars emerge, the nebula fades, and the cycle moves on. For now the veils drift away, dissolving into the interstellar medium, while the young stars remain, burning quietly, awaiting the long futures that stretch ahead. A sky reassembled takes shape when the nebula disperses, and the last remnants of gas and dust drift away into the wider interstellar medium. What was once a dense molecular cloud, a shroud of darkness and birth, is transformed into an open field of young stars. The glowing shells fade, the pillars dissolve, the filaments unravel, and only the stellar cluster remains, scattered jewels across the canvas of the galaxy. The irony is striking. The nebula that was invisible before star formation and luminous during it becomes invisible again once its work is complete. Another irony lies in permanence, for the stars, though seemingly eternal, will one day drift apart, their companionship lost. A third irony rests in scale, for the small cloud that produced a few thousand stars leaves behind a pattern of light that will be visible across thousands of light years. The dispersal is driven by feedback. Stellar winds from massive stars sweep away gas, ionization fronts erode filaments, and supernovae at the end of massive lifetimes scatter enriched material. The cloud that once resisted collapse now resists survival, torn apart by the very stars it created. Yet this dispersal is not destruction alone. The expelled gas rejoins the interstellar medium, carrying heavy elements forged in massive stars. Carbon, nitrogen, oxygen, silicon, and iron are spread outward, mixing into future clouds. The cycle of enrichment continues, each generation of stars seeding the next. The paradox is profound. Stars end the clouds that birthed them, yet in doing so, they ensure the birth of new stars elsewhere. The cluster left behind is young but already changing. Gravitational interactions between stars scatter members outward, while the loss of gas reduces binding. Some stars escape quickly, drifting into the galaxy as field stars. Others remain bound for tens or hundreds of millions of years, depending on the cluster's initial mass and density. Open clusters such as the Pleiades are remnants of such nurseries, visible long after their natal gas has gone. Eventually, even these clusters dissolve, their stars spread into the disk indistinguishable among billions. The irony here is subtle. Stars carry no visible mark of their shared origin, yet detailed chemical studies reveal common fingerprints, a quiet record of their beginnings. The process of dispersal reshapes the galaxy itself. Large associations of young stars illuminate spiral arms, creating the patches of light seen in distant galaxies. These associations are temporary, dissolving as stars disperse, but they maintain the cycle of visibility. The galaxy appears structured and luminous because clouds are continually collapsing, forming clusters and dispersing. Without dispersal, there would be no recycling of gas, no continuation of star formation. Without star formation, there would be no light. The irony is that the fading of one nebula ensures the brightness of the galaxy as a whole. For planets and life, this stage is crucial. Only once the veils are gone can disks survive in peace, unshaped by the harshest radiation. In quieter environments, planets grow from the remnants of disks, assembling into systems of variety and endurance. The heavy elements provided by the dispersal enrich these systems, allowing rocky planets and complex chemistry. The final irony is that the same process that destroys nebulae provides the building blocks of worlds, oceans, and living beings. Without dispersal, there would be no Earth, no observers to reflect on the beauty of the sky. The analogy is of a stage after a performance. The lights that illuminated the scene dim, the scenery is taken away, and only the actors remain, beginning their long roles. In the sky, the stars are those actors, set free from their backdrop, each carrying its own script through time. The nebula was the preparation, the brief drama, the luminous interlude. The stars are the enduring story, continuing long after the curtain has fallen. Observations of nearby regions confirm this transformation. In Orion, the great nebula glows today, but its gas will be dispersed within a few million years. The stars of the trapezium cluster will remain, drifting slowly apart. In Carina, massive stars already carve the cloud, and supernovae will soon accelerate its dispersal. In Taurus, smaller groups of stars form quietly, their gas dissipating more gently. Each region repeats the same cycle, with variations in scale and detail, but always the same conclusion: stars remain, nebulae fade. The quiet mystery of dispersal is how it sets the pace of star formation across galaxies. If gas is removed too quickly, star formation ceases and galaxies fade. If gas lingers too long, collapse may be inefficient. Feedback, dispersal, and recycling balance the rate, sustaining star formation over billions of years. The fine-tuning of this balance is not fully understood, and models struggle to reproduce galactic histories precisely. Yet the fact is clear. The dispersal of clouds is as essential as their collapse. Creation depends on destruction, and continuation depends on impermanence. The ironies remain steady. First, the brightest stages of nebulae are those of their destruction. Second, the permanence of stars is purchased by the impermanence of clouds. Third, the visibility of galaxies from afar depends on the continual vanishing of the very structures that give rise to light. The universe holds these contradictions without conflict, weaving them into a rhythm of birth, growth, dispersal, and renewal. As the sky reassembles, the stars shine alone, freed from their veils, each beginning its long journey on the main sequence. They will burn for millions, billions, or even trillions of years, depending on their mass. Some will end as white dwarfs, others as neutron stars or black holes, but all will outlast the clouds that formed them. The nebula is gone, the nursery dispersed, but its legacy remains written across the galaxy in light, matter, and memory. The nebula is gone now, its gas and dust dissolved into the wider interstellar medium, leaving only the quiet persistence of stars. Where once were filaments, knots, and veils, there is now stillness. The clusters remain suspended against the dark, glowing softly in their first stability, their fate set for times far beyond the length of any cloud. Around them, silence stretches, broken only by the slow drift of stars across the spiral arms. The echoes of collapse, of turbulence, of jets and sparks fade into memory. The chemistry of ices and the warmth of shocks are carried forward in the planets that may one day grow. The clouds that gave birth to them no longer remain, yet their dispersal has enriched the galaxy, spreading heavier elements into space. Nothing is wasted, nothing is lost, only transformed. Time stretches on without measure. Stars continue their long burning, each one a quiet lamp enduring where the nebula was fleeting. The rhythm slows, forward motion disappears, and what was dynamic now becomes calm. The galaxy turns, but here the pace is no longer of collapse or dispersal, only of steady light. The journey into the clouds ends in openness. The veils are gone, the shadows lifted, the hidden embers revealed. What remains is the quiet after creation, a sky reassembled into points of radiance, each one waiting out its long span. The silence is complete, and the stillness is lasting.